Okay, today I want to talk about computers real briefly, just a real little introduction to a couple of points where philosophers are interested in computers. Of course, that's something that we all hear a lot about, read a lot about these days. I think I can maybe show you a couple things that are interesting. Basically, I'm going to hit on 3 points. The first thing I want to talk about today is what it is about computers that strikes people as interesting in terms of thinking about the human mind and how valid this analogy is between computation and the human mind. That leads, of course, into the second point, which would be consciousness. I want to talk a little bit about the difference between intelligence and consciousness and maybe some of the implications that has in terms of thinking the computers do or do not have minds. And finally, I just want to give a couple quick opinions about AI. I know everybody has a lot of opinions about AI these days. Just again, a little brief introduction, try and find some fun links, and then set you loose to look at the relationship between computers and philosophy and computers and psychology this week. So let's start that with our slideshow. There we go. Again, no, back. Okay. Yes, what's that buzz? What's that buzz that we hear? What's the buzz about computers? We live in a computer age. We've seen a number of important points about that already. I pointed out, for example, that when we look at functionalism in cognitive psychology, we are certainly looking at a theory of mind, or functionalism really more of a methodology, that mental processes and properties should be described functionally rather than physically, aiming at a kind of transcendental cognitive or rational psychology. One part of cognitive science and psychology, not all of it, obviously. So philosophy and computers, let's take a look. In this picture, of course, in the foreground, you see Commander Data there, that pale fellow. Really what he is an actor painted white. But he acts like a robot, which is kind of interesting. On TV, you have a lot of characters which are actually humans acting like robots, which is interesting because what they're supposed to be are robots acting like humans. All right, so the first thing I want to say about technology in general, everybody has sort of different attitudes towards technology. And one thing about having any kind of sort of artifactual analogy with the mind is it's going to sound kind of reductive to some people. So you want to see if it's any good, the analogy is going to get at something that actually helps us understand the mind. But, we have to notice that, say, the ancient Greeks and Romans with their aqueducts and their living their lives at sea, they discussed the humors, the 4 humors, and they had this kind of vitreous or kind of aqueous, if you will, a picture of the inner workings. They saw it as kind of hydraulic relations between amounts of fluid, too much of this, not enough of that. And that reflected their understanding of technology that they used to causal effect. But someone like Thomas Hobbes, writing in the 1600s, the 1600s culminates in Newton's Principia. And these people in the early modern period had a kind of mechanical view of the world. So when they thought of the mind, they thought of pulleys and winces and bellows and things. That is, they just took the technology that they had and thought, well, the mind must sort of work like that. After all we can do is work with the conceptual machinery that we've got. And among that conceptual machinery will be whatever technology that we are familiar with. And it'll be functional, and we'll think about that in terms of the mind. So that's cautionary, because when we look at that, we think, well, in all past times, people also thought that their technology was relevant to the mind, and we might be a little bemused by some of their claims today. So we have every reason to think, don't we, that in future years, other people will have different kinds of technological attitudes and so on. And anyway, isn't it reductive just to say that, well, there's computers and minds are just computers, which of course they're not. All right, then. So there's a legitimate question that we're going to want answered sort of up front in trying to think about technology and philosophy and the mind and computers. And that is there anything about computers that makes them any different from aqueducts or wind-up clocks in terms of shedding some light on the way that the human mind works. Is there any way to think, is there any reason to think that looking at computers, we might be getting into insights that go a little beyond some of the insights of the past? And yeah, the answer is yes. And so that is what I want to explain to you today. We've been doing this class for a while. You know, I'm not a computationalist. I'm not even really a cognitivist. I don't even really think they're mental representations. But that doesn't mean that I don't see how computers are relevant to cognitive studies. They are. I'm going to explain to you how right now. The real key here is in digital computing. Why digital? What does digital mean? Digital as in ones and zeros. That's digital. So the point is this, what Turing and before him Leibniz, the first bullet point there, what they realized was that if you had enough capacity, so say you have ones and zeros, and you've seen these when you've seen ones and zeros printed out, lines of digital machine code, if they do that anymore. So you've got these long streams of alternating ones and zeros, maybe a lot of zeros, maybe a lot of ones, maybe a big mix of ones and zeros. What's going on? Well, the thing is, if you have enough ones and zeros, think of some combination of ones and zeros will stand for the letter A, one for the letter B, and so on. Others will stand for punctuation marks. But other combinations can stand for whole words and whole phrases and whole sentences, and whole books for that matter, as well as other kinds of algorithms and other kinds of transformational rules, which also can be represented in these zeros and ones. In fact, if you only have enough zeros and ones, that language, the language of zeros and ones, can represent anything. And the reason that that's significant is that is because it makes moving information around incredibly easy, because you have an incredibly simple device, one that only needs to distinguish between a 1 and a 0. In the case of a computer, that is a circuit that's going to let an electrical impulse either through or not through. So not through is going to be, if you wish, your 0, and through is going to be your 1, if you want. And this is why, since it's really a matter of putting together this formal digital representation, which is in the form of these long strings of pluses or minuses or zeros and ones or whatever you want to call them, then really all you ever need is more and more space, because the more space that you have, the more you can do it. And that's why the chips keep getting smaller and smaller. So, so what's the real takeaway here is that point about digital computing. Why? Because in a digital machine, what you have are in the circuits gates. The gates are open or shut. Those are your two states, your two machine states. So the zeros and the ones, then notice, are actually descriptions of the actual physical state of the physical object, the machine. That is, they are actually showing you gates that are letting through or blocking electrical impulses. Each 0 and 1 stands for an event like that. So that machine language meaning the description of the actual physical object. And then the digital code is the connection between that machine language and the formal languages that supervene on it. So the images on the screen, the stuff that the print that you're reading on the screen, and all the rest of it. So so that's how it's done. And so the question then is going to be, now the question is really going to be something about a question about the brain, right, rather than the computer, because now what we want to know is, well, okay, so a computer does it that way. A computer is a digital device. The way that the computer represents information is digitally. Okay, so its representational architecture, if you will, is digital in form. It moves information around in the forms of strings of alternating zeros and ones. So now what we want to know is there anything about the human brain that would lead us to think that the human brain works in anything like that way? And actually there is, and actually it's interesting. Again, I'm not a gung-ho enthusiast for even for computational or even for representational accounts of nervous system function, but this is something that you should understand if you're interested in research psychology. Well, here's just a circuit. Again, the circuit's a little chips inside the computer. The smaller you can make them, the more information they can store and process. So neural cascades and graded potentials. Let's talk about brain neurophysiology for a sec. So you've got neural cascade. What is that? Well, an electrical, like the brain is an electrochemical device. So electricity is conducted through it in various patterns. That's how it does its thing. So what's a cascade? Well, think of a waterfall or a pachinko game. Maybe you've got an electrical event at some point in the nervous system, and then it has downstream neurons from the neurons where the electrical event has initially occurred. There are neurons downstream, and they get this activation signal. They get the electricity coming down the line, and then they go into their own state, and they have their own dendrites, which are the little small filaments that come out of that end of the neuron and connect it to other neurons in other places in the brain. Well, so then what you have is that the way that the neurons are connecting with each other is basically, you can think of it this way, gross oversimplification, of course, but we're trying to look at the sort of conceptual architecture here, that one nerve cell, one brain cell is getting a stimulus from another brain cell. That is, it's either getting a stimulus or it's not. And there's your binary structure. That's what sort of looks binary. And by the way, the neurotransmitters that you always hear about, like serotonin reuptake inhibitors that you take for depression and that kind of thing, those neurotransmitters are buffering the cleft, the synaptic cleft. What is that? The little space between the nerve cells, and they make it either more conductive or less conductive. Like if there's electricity around and there's a pool of water on the floor, that's a little dangerous because the electricity might conduct through the water, right? Well, the idea here is you have sort of basically four groups of neurotransmitters, and they're increasing or decreasing the conductivity that exists between the one neuron and the other across the synaptic cleft. So why is that significant? Well, because think about 1 and 0. Okay, so you've got a switch that it's either on or off. All right. Now compare a switch that's either on or off to, say, a dial on a radio where you have between 1 to 10, or if you're in spinal tap to 11, and you can turn it all the way up or you can turn it down. There are these gradients. And so that's many more states. The switch can only go on or off is 2 states, on or off. But depending on how finely you can measure it, a gradient like that, like a volume switch, a current alternator like that, is got a very, very large number of potential states. So you may have heard it said that the human brain is the most complicated object that scientists have observed in the universe. And you might have thought that means that with its hundreds of millions of neurons all bundled together in extremely complex shapes and forms all through the brain, and many different kinds of neurons. But actually, it's not the structural complexity that scientists are talking about if they say that the brain's the most complex. What they mean is the brain is the most complex object that we've observed in the universe, including in human artifacts or anything else, by the way, because of the potential number of connective states it can get into. Think if you have 7 little points and 2 of them might be connected, or 1 of them might be connected with 2 others, or these 2 over here might be connected and those 2 over there. So among the 7 nodes, think of how many different connective possible states there are, between them all being connected, none of them being connected, everything in between. It's very, very many. Now, it's a crude analogy, but think about the brain with its millions and millions of neurons. Obviously, they can't all communicate with each other. They're all dedicated, and each one communicates with specific other areas of the brain. So, so that's what's meant by saying that it's the most complex object. And so anyway, the takeaway though right now is then you can see how digital information processing is interesting when we look at the brain, because we see that essentially it looks like the way that the brain functions is by having activation states between units, between neurons. And so that looks like, similar then in sort of its causal structure to binary computation. Here you see again the synapse is in the little box there, and you see the input is coming in on the left, and then going out and in through the axon, and then going out through the dendritic tree to all the downstream neurons. And this is how electrical events go cascading through the nervous system. They used to cut the corpus callosum, the nerves that connect the two hemispheres of the brain, as a very sort of crude and violent treatment for epilepsy. But it worked because it would keep the electrical storm from crossing over into the other hemisphere and causing a general seizure. So here you see that little box with synapse. The synaptic cleft is actually what you call the actual space. A synapse is an electrochemical event between two neurons. And here you see that close up again. There are these, we won't go into any further than this. All you need to see from Mr. Philosopher here is that it looks like it's sort of it is indeed a sort of on or off thing where one unit is sort of getting stimulated by another unit, and that's forming patterns. And that's all we really need. Because neurophysiology has, in fact, had some impact on computer architecture. This was really exciting stuff in the 60s and 70s, during the time when people would really talk about neural net modeling. Neural net modeling being, as the name implies, actually computer engineers being inspired by neurophysiology. So it's not all been just neurophysiologists looking at the circumstantial evidence of computer technology to make inferences about the function of the neurophysiological structures. That's true, but it's also computer engineers taking away lessons from looking at the way that the nervous system accomplishes some of these things. It used to be called PDP, parallel distributed processing. Mostly that exists now in sort of SETI and stuff like that. But nowadays we call this connectionism. I'm going to explain connectionism to you now. And so here's a really important part of today's lesson for people in the class. We've been talking all semester long about empiricism and rationalism, about rationalist psychology and empiricist psychology. And the fact is, amazingly enough, that the divide between the rationalists and the empiricists, we find once again in computer science and computer architecture, where there are two basic approaches: the top-down approach of classical computation, where you have formal rules that are formalized, what does that mean? In symbols that are followed, and connectionist systems being self-learning systems a la empiricism. The nodes are the connections between one layer and another of the computer, but the nodes also are the things that get stimulated, just like the neurons. Think of the nodes like the neurons. They are the connections themselves, and they are the things that are activated or not. So here's a simple connectionist model. Again, the input on this model and this schematic is on the left. And then there's hidden units that are going to, these can be weighted. So you get maybe a signal from this one and a signal from this one. If you get enough signals coming in, you'll activate the downstream node. And if you don't get enough, it won't get activated. And that's the way you can get positives or negatives. This technology was originally developed for radar and sonar. So you want to be able to tell, say, on a submarine, if you're looking at a school of fish or a mountain under the water or another submarine or something like that. Today, very ubiquitous in terms of facial recognition software, for example, or in the post office, the software that's used to recognize letters and handwriting. Imagine how difficult that is. And that also now is done by trained connectionist machines. So obviously you can get much more complex one. Here the input layer is on the bottom, the output layer is on the top. Again, they're weighted. You think of weighting as sort of positive and negative reinforcement. You're trying to get your system to do something after all. It's a human artifact and it's got a function. So as it learns by trial and error, what learning is that its human handler is showing it, is weighting it, showing it what things are important. So again, rationalist computation and empiricist computation for us as, basic philosophers of psychology, students of the philosophy of psychology, this is what you really want to understand. Connectionist systems aren't like Kant. Classical systems are. What does that mean? As you should know by now, Kant then thinks that there's this conceptual scheme that's in place prior to experience with its rules, its transformational rules, and so on. And what it is to have a mind is to follow this framework. This framework provides that possibility, according to Kant. Here we have a Humean computation, right? Empiricist computation in the connectionist system, which is trial and error, law of effect. When it gets a good result, that's reinforced, then it becomes more likely to get into that connectivity pattern again, which, by the way, appears to be the way that memory works also in the human nervous system, that in a memory, the same neural circuits are activated. And every time a neural circuit, a neural connection is made, it makes a chemical change in the neurons such that it's easier for it to happen again. So again, just a huge takeaway from us, because what we want to understand is this rationalist empiricist distinction in psychology. And then we come along here to computers and we notice that sure enough, there it is. Last bullet point on the slide. For me, connectionist machines are important because, as you know, I'm skeptical of representational models of mind. That's sort of my thing. So that's a reason for me to be interested in connectionism. And I'm one of the 3 people here at Kalehi who does the interdisciplinary course on artificial intelligence, if we do that again. Number 2, though, and getting to the last thing I want to talk about today, getting almost done here, that is that this self-learning is really the key to understanding AI. AI, by the way, I mean, philosophers do conceptual analysis, right? And then think about what words mean. And this popular phrase, AI, standing for artificial intelligence, has actually really been going through some changes in recent years, mostly due, I think, to social media. And I think that what AI is coming to mean is feedback software that sort of anticipates what you need rather than anything else. And that's a much more specific notion of AI than what it used to be. So for example, I say, well, I like the music AI on YouTube better than on Spotify or something like that. So there's shifting senses of the word artificial intelligence. I just want to make a couple remarks about it. What I'll make here before going to the next slide is really what's kind of scary about artificial intelligence right now is not that the robot army is going to revolt. What's scary is that it's just really, really powerful technology, and what's powerful about it is the way it can learn in this way. And so when you have huge networks that are geared towards promoting certain things, selling certain things, gathering certain kinds of information, and it's that mass effect of the cross-referencing, really, the movement of the information, that actually is the most dangerous thing, I think. I'm not, especially down on it, but there are some dangers, but that's what it is. It's not like the Will Smith movie. Second main point here, computers and consciousness. As I say, we've talked about this before. If you're not familiar with John Searle's Chinese room argument, you should check it out. You may or may not find it persuasive, but you should know about it if you're interested in arguments about computers being able or not being able to have minds. So part of the question there is, what is a mind? And you might say, well, being intelligent, as this phrase artificial intelligence implies, but having a mind, as Searle points out in the Chinese room, seems to also involve having some sort of qualitative awareness, even a kind of evaluative qualitative awareness, that is, that one is experiencing things as being sort of nice or not so nice, good or bad, right? As well as knowing that peach means something and being able to fill that in. You know, a computer doesn't necessarily know that the symbols are even symbols. The computer is just matching the symbol to the other in a law-like way. So a computer is just not got any awareness that it's about anything at all. There's no reason to think that it does. What's the mereological fallacy? That's the fallacy of mistaking the whole for the sum of the parts. We're making the mereological fallacy, for example, when we make a traditional Cartesian homunculi out of the brain. So nowadays, people trying to be materialistic and naturalist, they're trying. And so what they'll do is say, well, it's all the brain. It's the brain that's solving problems. It's the brain that's recognizing patterns. It's the brain that's comprehending and producing speech. We even know where it's doing that in the left hemisphere, right? In Broca and Wernicke's areas. But no, that's not right. Human beings, whole human beings standing right in front of you, embodied in their environment, comprehend speech, produce speech, recognize patterns, solve problems, think, dream, aspire, and so on, feel. Chunks of brains don't do anything like that, okay? So how does that have to do, again, with computation? Well, when we're looking at consciousness, and I'm thinking it's pretty clear that computers don't have anything at all like consciousness. Does that mean that I don't think that there could be a conscious artifact? No. Metaphysically, ontologically, I'm a monist. That means that it looks to me like a physical object. It looks to me like I am a physical object, if anything is. And therefore, then any other physical object that had the relevantly similar causal properties that I do will also have consciousness. So it also follows on that naturalistic monistic view that a conscious artifact is theoretically possible. And I believe that's true. But I don't think that we're doing anything. I don't think that computation or computer science or computing is moving in anything like that direction. I don't think it's making any progress. I don't think if you work on computation long enough, you get a conscious thing. No, I don't see any reason to think anything of the sort. It looks to me like we might get conscious artifacts, again, not artificial consciousness, but conscious artifacts, if we do, through something like robotics engineering. Because, for example, the reason that when I say I'm conscious, I have all these sensory organs, all these nerves all over the surface of my body, all through my body, really kind of raw. And so, right, that's what consciousness sort of is. And that is hardware. It's being embodied with all of the stuff that's sensitive to my environment, all the hardware that's built into my body that's sensitive and reactive to the environment. And that's really what consciousness is. It's not a species of computation. There's a lot of computation involved when the light gets to my retina, and my retina has to convert the input into some kind of electronic signal to send up the optic nerve, to speak in representational terms, right? It looks like you got a little onboard computer at the back of your eye. It looks like there's a bunch of little onboard computers all over the place, certainly in your nervous system. But that doesn't mean that the mind is a computer. And again, I just showed you why I doubt that is. When would we decide that we had a conscious artifact? I think I think we sort of know it when we see it, the way we know it when we see it in dogs and cats, or maybe distressed bugs, flies. Um, but it's going to be when the reaction and awareness and sensitivity to the environment is such that we come to see it as goal directed in terms of avoiding the bad experiences and trying to obtain the good experiences the way we do with other human beings and dogs and cats and aliens from outer space. And when that comes, then I mean, we'll see them as legitimate recipients of moral concern when I think when they are. I'm really not worried. I think that's something that's pretty elemental, but it's a very informal thing for me to say. So, okay, finally, then just a couple of points about artificial intelligence, and then I'll give you a bunch of links and set you loose to make what you will of computers and philosophy for this week. The phrase artificial intelligence is a bad phrase. It's like the phrase artificial music. I mean, I sort of might know what you mean. You mean it's computer generated music, maybe, I guess, or something like that. But what you don't mean is that it sounds like music, but it's not really music. Because sounding like music just is what music is. But intelligence is just like that. It's not, oh, well, it seems as if this being is intelligent. Seeming intelligent just is being intelligent. I mean, unless maybe you're remotely controlled, you want to play some sort of silly game like that. So, so intelligent artifact is the right one, right? I know everyone's going to keep on saying artificial intelligence. I'm going to keep saying it too. I just live here too. I'm humble. AI. But it's not right. I mean, intelligent artifact is what you're really talking about. Anyway, the other thing, look, as I've been stressing, mind is a heterogeneous concept. You have intelligence. I think that we can, I think a thermostat, as this is an old argument in philosophy of science, I think a thermostat is conscious. I mean, again, what are its beliefs? If it's got a filament that expands and contracts depending on the temperature, so it either makes the connection and turns on the heater or it doesn't. So it either thinks it's not too cold or it thinks it's too cold. You say, well, it doesn't have any experiences at all. We'll put enough function together and put enough, as I say, put the structure together so it's sensitive enough to its environment, which the thermostat is, right? And that's what consciousness is, okay? That's what consciousness is. So then finally about the dangers of AI. The dangers of AI, I talked about a little bit before. Why do I think what I think? I don't think that the dangers of AI are that sinister machines, or even not sinister machines, are going to come to have their own lives and their own goals and leave us all behind because they're so smart that they kick our asses even though they didn't mean to. Nah, I don't think anything like that's going to happen. Why not first? And then I can go on to what is dangerous. Why do I not think that stuff is dangerous? The sinister robot from the Will Smith movie. Because roughly, here's why. Because computers don't have qualitative experiences or life cycles, unlike animals, say mammals. And that is, there isn't anything actually that's good or bad for it. A microorganism that has no mental experiences of any sort that we would think of, nonetheless, a living thing. If it goes up too much, it's going to die. If it goes down too far enough, it'll reproduce. So now it's getting selected for the ones that move in the right direction. Is that the beginning of consciousness and intelligence both? Yes, it is. Sensitivity to the environment. And everything is on a smooth continuum from that unicellular organism up to you and me. Okay. So a computer then, I mean, I say my car doesn't like the cold weather or my car wants this. I know I'm talking metaphorically. This is what Daniel Dennett calls the attentional stance. He's not making the same point with that I am here. He's probably making a much better one. Right, but that's because I don't understand the computer well enough. I mean, the car. I'm sorry, the car. If my cousin understands the car better than I do, which he does, then he'll explain the same thing, not in those mental terms, because he doesn't need to use them. Right. So you can talk about a computer that way, but that's all you're doing. Somebody else, a computer engineer, wouldn't need to talk about it in intentional terms that way, any more than the car mechanic would need to talk about the car in intentional terms. The computer's more like a rock than it is like a dog. The computer's like a magazine or something like that. It's a prosthetic that you use to store information and move information around, and a few of us even to compute, not me. So, okay. So are there going to be these intentional robots that just want to go off and live their own lives and screw the humans? Nah, I'm not worried about that at all. Finally then, sorry about that, but finally really quickly, what is dangerous? What's dangerous are these unforeseen consequences of massive computational power. A number of different things happen. One thing is that you get these algorithms, which are, again, they're just really, really massive, identifying people's likes and dislikes. And there are tons of unforeseen consequences in that, not just privacy concerns, although there are terrible privacy concerns. Right now, for example, if you wanted to know, well, who are the Lutherans who have a professional interest in Japan who might consider voting for the Libertarian Party in Minnesota? And I bet there's more than one. But what I'm saying is the database that's in place right now can easily be used to generate that list and many others. So there's this abuse, human abuse of artificial intelligence. Human abuse is the big danger. And then the other danger, which is not necessarily human abuse, but which is unforeseen consequences, are these movements of information or promotion of information, amplifying things just automatically because of these algorithms on social media that no one's in control of. And that's even something that's just starting to be discovered now. But these are all, like environmental pollution, dangers from computers are not, they're not like dangers from outer space. They're like dangers from polluting your information flow and like putting other, toxins in your environment, that kind of stuff. Anyway, so like I say, something to think about this week. We're thinking about all things philosophical and computational.